Okay, here we are in the Origins podcast for one of my favorite times every month when I get to speak to one of my favorite people, Sabine Hossenfelder, and I get to hear her unique take on science, and we have a discussion of science topics in the news, what's new in science, and it's something I've come to really enjoy, and I'm really happy to say, as far as I can tell, other people actually enjoy it too. So Sabine, how are you doing there in Europe? Is it hot?
Today's fine. It's actually raining outside, so yeah. Well, good to see you, and good to see you in the studio this time.
Yeah, that's right. I try, following you, I try and up the game a little bit because you're always so professional. So it's nice to be in a studio. Thank you. Well, we're going to talk about a bunch of interesting cosmic and terrestrial topics today. And speaking of terrestrial, you're going to talk about a topic that's supposedly going to change the future of the world. So why don't you talk about that?
Yeah, I want to talk about hydrogen. So this is a topic I've followed for a long time because I have a personal grudge with the German government that's
Uh,
invested a lot into this so-called hydrogen economy that isn't going anywhere. So I have a lot of misgivings about this stuff because I've always said like it doesn't make any sense. Like to
mhm.
begin with, um, the idea that we would produce hydrogen from renewable energy and then use that to, create electricity. It's terribly energy inefficient, so it doesn't really make any sense.
Yeah.
And so in practical terms, what actually happened is that we're paying taxes for what's been called the hydrogen ready power plants. What what are they? They're actually just gas power plants because once you have something that can deal with methane that has a lot of H's in it, it's not that difficult to switch it to burning hydrogen. So and hydrogen has a lot of problems that I don't want to go through the whole list. But besides the energy efficiency, I think that the next biggest problem might be what's been called hydrogen embrittlement. Like whenever you want to store the stuff or you want to push it through pipes, you have this issue that hydrogen is the smallest of all atoms. And so it creeps into everything and destroys the material sooner or later. So I think that this is going to become a maintenance nightmare, which is also going to drive up the
Let
cost.
me let me interrupt for 1 second just because
All
we
right.
we know it, but just so people know, you might in light of what the things you said already, might say, "Why hydrogen at all?" But the whole point initially is hydrogen burns with oxygen to form water and releases energy, and therefore there's no carbon dioxide, there's no bad byproducts. That's why there's no fossil fuel byproducts, and that causes the initial excitement about hydrogen and why there's so much verbiage. And I'll also say I used to speak out against it because in the old days, when I did, people didn't realize that, it sounds great, except you get the hydrogen from fossil fuels. So you end up in the old days, you used to, so and end up it was a scam because you didn't save any carbon or anything to get the hydrogen. But things have changed. So anyway, just to preface where you're at. Go on.
Yeah, that's right. At the moment, we get almost all the hydrogen actually from methane or coal in some cases, because there are all these H's in there. But if you have methane, that's CH4, you also have the carbon. And so if you split off the hydrogen, you're left with carbon dioxide, which is exactly what you don't want. And so this is why that's the idea. We produce it from renewables, like from solar or wind or something, and that just isn't happening. And even if we would manage to get it done, it'd be ridiculously expensive. So I doubt it'll ever make sense. Um, Nevertheless, the German government and also the many European countries and also the United States, by the way, have put a lot of money into this so-called
Right.
hydrogen economy. So there's one possibility to make sense of this, which is if we were to find naturally occurring reservoirs of hydrogen. This has been called white hydrogen, not actually referring to the color of the stuff, but just they have a color scale that tells you where the stuff comes from. And so this white hydrogen is something that you can find in the ground in some places, like natural gas, like methane. And so it gets stuck in like porous rocks, and then you can drill into it. And I actually don't know exactly how it works, but they get it out of the ground and they can use it. And so the issue is just that so far there's been only one place where they actually do this, which I think is in Mali or somewhere. So it exists, but it's been believed to be really rare. And then, like 2 years ago, there was a group of French researchers that claimed they'd found a reservoir of white hydrogen, actually pretty close to the border to Germany. And just like 2 months ago, they claimed they had found a second one a little bit further north. Yeah, so big if true. Like you said, we haven't actually
Right.
seen them extract anything from the ground. And then the other thing that happened was a group of geologists went and tried to generally analyze like the possible abundance of the stuff in the ground based on what we know about how those rocks formed. There are different ways that hydrogen could be formed underground. For example, because um, water comes into contact with some very hot stones that contain certain minerals, and so it gets split into hydrogen and oxygen, and the hydrogen then embeds in the stone, or it could happen through radioactive decay and some other possibilities. And they just produced this global map where they said, look, in these places, it's possible that you can find something, and they estimate that all these hydrogen reserves combined could power the world for 100,000 years. This is why I say big if true, right? So,
Yeah.
of course, just because you put it on a map doesn't mean you can actually extract it. So, there are lots of ifs and thens there. But honestly, to me, it was like I got this feeling like we might have underestimated, if not, with an actual mathematical
Mhm.
estimate, but unconsciously, how much of this stuff might already be lying around. So if it was true, and we could just, even if it's just a fraction of this, I mean, even if it lasts for 100 years or something,
Yeah.
that would be a really big deal. And
Yeah.
there are a lot of startups. I mean, the saying a lot is maybe is saying too much, but a couple of startups were trying to look into this and are actually trying to extract this white hydrogen. So I think that's a very interesting development.
Yeah, I think it is. I mean, I learned about it from you, and I was looking at that paper you mentioned a little bit, and I was intrigued because it does make sense. I many years ago when I was trying, I first proposed we look for antineutrinos from the Earth to do geophysics, and now people do it. But this was 40 years ago. Um, there are lots of interesting processes, radioactive processes, but other processes. And let's face it, there's lots of, when I think about deep ocean vents, what comes out of there is hydrogen sulfide. There's lots of hydrogen coming out of those vents. So when you think about when I saw that, I thought, it makes sense. There probably is a lot of hydrogen that may come out. And but as you point out, it's a long way from maybe having it to making it practical and useful. But it does at least it made me feel a little bad because I used to make so much fun of the hydrogen people by saying, "Yeah, first you get gasoline, then you you burn it to get hydrogen, and then you use your free clean hydrogen." It was just it seemed like a scam. Plus, it's a little bit dangerous to transport, but as you said, also, it's very invasive. But one thing that did occur to me, I do wanna ask you this, you sort of mentioned it as a negative, but if we had so much hydrogen we didn't know what to do with it, then if you had something like fission or I mean, if obviously you had fusion, it'd be different, but even fission, something that, the problem with fission plants and fusion plants is you produce electricity, which is not a problem, but it's nice. But you do sometimes, until everyone has electric cars, you don't necessarily use electricity. And if you had hydrogen and combined with oxygen, you would be able to power as fuel cars. And so it occurred to me that um, maybe if we had a lot of some kind of um, renewable or carbon-free power source, then splitting hydrogen and oxygen from seawater, which is very energy intensive, if we had a surplus of energy, it might not be completely crazy because not all forms of energy we need are in the form of electricity. You may want to have fuel. And we don't have these grids that allow you to move electricity and batteries that allow you to store it. So if you could convert what would otherwise be electricity to hydrogen that you could use as fuel locally in your car or in a power plant, it might not be so crazy. I was thinking about it. What do you think?
Yeah, I think that's totally correct. In the end, I think it'll come down to how expensive is it. But
Yeah.
like this is the most practical application of hydrogen that people have thought of. You
Yeah.
could use it for transportation, um, for example, in big trucks or something, because
Yeah.
these hydrogen tanks are kind of heavy.
Yeah.
So for for stand-up passenger cars, it's maybe not so great. I mean, they do exist, but they have some downsides. But if you have a big truck that weighs some tons already, it doesn't really matter, basically. And the other thing is that you could use it to store energy.
Yeah.
So this is one of those things where, for example, in Germany, there was supposed to be a project where they had these offshore wind turbines that were supposed to
Yeah.
produce hydrogen, and they wanted to pump this through some pipes to somewhere on land. And so if you have a surplus of energy from there, you can store it in the hydrogen, and then you can use it when the wind doesn't blow.
Yeah.
Basically,
Yeah.
that was the idea. I'm not sure what happened to this. The issue with all these things is that, um, you know, they're too expensive,
Yeah.
and so especially in Germany, like we have all that coal, like, and then it's dirt cheap. So why don't we just dig up some more coal?
Yeah.
So
Yeah.
it becomes a big political problem.
Yeah, yeah. Well, that's the problem. I mean, that was always by the way, my concern about fission. I have no problem. I don't have any safety concerns about nuclear reactors, well-designed nuclear reactors. But given all the regulations and everything else, they're just damn expensive compared to certain things. And so it was an economic question for me as much as anything else. But yeah, but the idea of storing it until we have good batteries or a better infrastructure nationwide to transport electricity, if you transport it as hydrogen and then turn it into electricity here where it might work. On the other hand, if I saw a truck that said hydrogen, and I think I've seen them, I tend to try and steer clear of them, having been remembering the Zeppelin episodes from the old days. It is kind of flammable. Anyway, okay, so much for terrestrial hydrogen. In a sense, I want to move now to the cosmos, cosmic hydrogen, which is one of the things. And cosmic hydrogen exists mostly in the form of stars, or a lot of stars and galaxies. And it leads me to the news of the month, which I think is probably the biggest story I heard reported among the news of the month was the opening up of the Vera C. Rubin telescope in Chile, which is named after a lovely woman. I knew Rubin, and her story is poignant. As a young woman scientist, had a hard time to be a young woman scientist, but she never harped on that, and she did her work. And Vera Rubin was one of the first people, not the only one. Tends to get most of the credit now, but not the only one to first argue that there was dark matter in our galaxy by looking at the rotation curves of our galaxy and other galaxies, looking at hydrogen lines and hydrogen gas clouds, and making an argument which at the time many people didn't believe, that our galaxy was rotating too fast, and now we see most other galaxies are, and you and I have different views of what might be the cause of that. But anyway, I'm very happy it's named after her. She was a lovely woman and a good, really good scientist. But it's a telescope in Chile, 8.4 meter telescope, which is pretty big. And first of all, it's nice to see a new telescope being built. Living in a country, I don't live in the United States, but living next to a country which can't seem to build a big telescope because it might offend some deity of some weird indigenous group that have land on it, and the 30-meter telescope is now a dead project probably in the United States, and the Trump administration wants to kill it anyway. It's nice to see a new telescope being built, and it's a very different type of telescope. It got a lot of press because it produced some pretty pictures, which is generally what telescopes do for people on the ground. That's what people like about them, is the pretty pictures. It's not really designed to produce these pretty pictures. It's designed to scan the entire southern sky every day, every 2 or 3 days for the next 10 years to make what, if you were to look at it, might look like one of those most boring 10-year-long movies you could imagine. But if you're a scientist, it could be interesting. The idea is that it's got this incredibly big field of view. It essentially 45 moons worth of the sky at any one time, as opposed to the James Webb Space Telescope, which has also got a pretty big field of view, but it's like one moon. So, and it moves faster than any other terrestrial telescope without jittering, and therefore it could see the entire sky every 3 nights. And it has the largest camera in the world, a car-sized camera, a 3.2 gigapixel camera, um, which, maybe, which is always amazing me to think about, because I know in 10 years, you and our iPhones will have 3.2 gigapixel cameras. But right now, a 3.2 gigapixel camera is it's almost 100 times bigger than the camera in your iPhone. It produces a single image that would, in order to see it adequately, require 400 ultra HD TVs. And each image, each night, it produces 20 terabytes of data, which is more than the information in all the world's books. And so it sounds great, and it's because it's fast moving, you can see things, but because it has such a big field of view and it looks night after night after night, it can look for transient events all over the sky. And it's already in one 10 the data they released was only the first 10 hours, which already allowed them to see 10 million galaxies in that big image, but also discover all these asteroids because they can actually see them moving through the system. And so it sounds great, and I'm sure it will be great, and it's touted to do many things. Of course, like, it's almost a de rigueur, it's almost a required, constitutionally, for every one of these telescopes to say that they're gonna learn about dark matter and dark energy as a result, and I think you and I are more skeptical sometimes. I think it'll actually, to be fair, because it has such a big field of view, it'll look at something called gravitational lensing. It'll be able to see lensing very, very well, and that at least does map the gravity of field of galaxies. So maybe it'll reveal stuff about, dark matter. I'm still not convinced about dark energy, but it actually may be most useful for saving our lives in the long run, because it's gonna discover thousands of new asteroids, some of which may be on a trajectory of on Earth, uh, an Earth crossing trajectory, and maybe give us enough time to save ourselves one way or another. But I don't wanna make too much light of it, because it is a new window on the universe that particularly is good for seeing a lot of things at once and transient events, supernovae, pulsating stars, and it may be useful in integrating with gravitational wave detectors, because it's gonna be able to look in real time very fast for odd signals. So when a gravitational wave detector sees 2 neutron stars collide, the gravitational waves, it might be able to tell this telescope where to move. And since it's such a big field of view, even if you can't localize it very well, this telescope might see it. So it's gonna improve astronomy, and I suspect what it will discover are things we don't expect, because every time I open a new window on the universe, you're surprised. And the usual suspects like dark matter and dark energy, I expect won't be changed revolutionarily by it. But it's really exciting to have a nice new telescope that does something very, very different with neat new technology, um, especially if you like neat new technology. So, and it has produced a few interesting pictures. And if and I and all I for all I know, there's going to be some nerds out there in Germany who buy themselves 400 HD TVs, put them up on a big screen, and see a picture from the Rubin telescope someday. I don't know. What do you think?
I think you've said almost everything. And I've thought very hard about what I could possibly add. So I have one thing to add, which is that they put out an app which is called the Sky Viewer app that allows you to. So I don't know if that'll go through. So you can zoom in your
Yeah.
high definition picture, and I think they plan to add some annotations, more details about what's going on in these pictures. Like this one is very pretty.
So
No
you already
idea
have
what
the
I'm
app. I didn't
looking
even
at.
download it. You're so much younger
Actually,
than
I
me.
think it opens in the browser. So like skyviewer.app, I think that's just a website.
Oh, I see. Oh,
In any case, so I mean, you kind of said this a little bit dismissively, like it puts out pretty pictures.
yeah.
But you know, I think this is kind of really important for science communication. Like you have something to show, something that people can relate to, and people just really like these images. I don't see anything wrong with it.
Oh, it
And
excites
so
kids. Even if it excites kids to study science in school, it's great. I mean, I
Exactly, exactly. So I think it's great they put out something like this. I hope they'll make a little bit more of it. Like this
Mm.
seems to be just you know the core of an
Yeah.
idea, so, where there's more to come.
And, and if they did something like that, I have always mixed feelings, but it's not bad. There's citizen science too. So if they have an app and they've got these huge images, they can encourage people to look in the images for things that I mean, I'm sure their data analysis and their AI, mechanisms are good, but you never know. If you allow few 100,000 people to look at these images and look in them, maybe people will see fun things that other people can't. So yeah, I think it's wonderful. And it does illustrate a few things. I mean, space telescopes are very important, and I'm very sad that the next large space telescope, the Roman Space Telescope, which is essentially built and paid for, may not fly because the Trump administration has decided science is bad. No science. No science makes the world a better place. It's apparently what the Trump administration has decided, because scientists are bad. Because scientists are bad because of money that are liberal. Therefore, science is bad. Therefore, kill all the projects that have already been done. But anyway, that's a little button for me. But the next space telescope may not fly because at least the current administration doesn't want to budget money for it. But it's lovely when you can see how much you can do on Earth with new telescopes, and they're expensive. This one was actually less expensive than I thought. It was under $1 billion. I think it was $800 million. The, next large telescope, I think the Magellan, I think it's called the Large Magellan Telescope. Anyway, it's probably more like $5 to $10 billion, but, which is the scale. This is 8.4 meters. The larger telescopes are tens of meters across, like this, you know, 15 to 20 meters across, and they're incredible. And I'm still amazed, you know, I had a telescope when I was a kid. I still have a telescope. I never do anything really great with it, but it amazes me that here on Earth, you can look through the atmosphere and see all of that, that it's all out there. It's just it is so inspiring. Anyway, yeah. So if it does nothing other than inspire young people to uh to get interested in the universe, then I'm all in favor of it. But it'll
Who
do more.
knows? Maybe we'll finally discover extraterrestrial life.
Yeah, well, it's certainly there for transient phenomena one way or another. My friend Jeff Marcy and his colleagues are big on saying that the best way to look for SETI is not radio waves, but to look for optical transients. And maybe this will allow us to do that. There's certainly going to be a lot of data, 20 terabytes a night. I wouldn't want to be the data that the person who's in charge of that data set. It's amazing. Well, from the immediate and in front of your face science to the esoteric science at the limits of knowledge, literally and metaphorically, I'm told that you have a very interesting paper that you read.
Yeah, yeah. And one of the authors of the paper is also very in your face. You put out a paper together with some co-authors
Mhm.
that argues that a theory of everything isn't logically possible. So that's my brief summary,
Yeah.
quoting some mathematical theorems. And I want to back up a little and explain in which sense you use the phrase theory of everything, because there are several different
Yeah.
things that it could mean. So, in the narrowest sense of the word, physicists talk of the theory of everything as something that unifies all the four known fundamental forces. So, the three forces in the standard model: electromagnetism, the strong and weak nuclear force, and gravity. Um, and that, in principle, should explain everything, hence the name. So, in practice, of course, it's not going to, allow us to predict human behavior or something like this, because even though people are made of particles that are determined by those fundamental forces and the interaction between the particles and everything. We can't actually calculate something as complicated as that. But in principle, it'd be a theory of everything we know. And of course, physicists hope that it'd also include dark energy and dark matter, and that might pan
Mm.
out, not pan out. I think that in your paper you use the word in a somewhat more general sense, which isn't just that it needs to combine these four forces, but is actually also a final theory, which I think a lot of physicists believe and certainly hope, which was maybe best captured in Steven Weinberg's famous book "Dreams of a Final Theory."
Yeah.
There's this idea that we're pretty close to the end of physics in some sense, because we the only thing that's missing is this unification of all the forces. And yeah, that sounds very similar to what Lord Kelvin said like 150 years ago,
Yeah.
which I
Yeah.
paraphrase: "We're almost done with physics. Just some little niggly bits left to sort out." That
Extra decimal points.
or
Yeah.
quantum mechanics and the entire starting model, right? So yeah, so I don't really believe the stuff with the final theory. But so this is why I read your paper, because it plays to my confirmation bias. So basically, in a nutshell, I think the argument has like three different points. The first is Gödel's theorem that I think most people have already heard about. Roughly speaking, it says that any such theory, if you can write it down in innumerable axioms and so on, so that there are some
Mm.
checkpoints that it needs to
Yeah.
fulfill. But I think those are actually fulfilled for the theories that we use in practice. Then that theory will have statements that are true, but that you can't prove to be true. So
Mhm.
that's a little bit awkward, if you want your theory to give answers to everything because it's a theory of everything, then actually you can prove that's not possible. And then the second argument is kind of related to this, but it builds on a different theorem that says, well, for any such theory, you can't even construct a function that'll tell you what is true and what isn't true. And then the third step is a complexity bound. So whatever theory you have, there's a limit to the complexity of statements that you can make, roughly speaking, and you can't tell exactly where it is.
Yeah.
You don't even know, and that's a little bit awkward because it could be that nature is just above that bound. So what kind of theory of everything is that if it actually can't explain that thing which is above the complexity bound? So I think that's a very interesting argument. And honestly, I think that this is kind of an approach to the mathematics that we use that I think physicists should use more often. Like so there's strictly logical argumentation about what's even theoretically possible, where are the limits of our methods. That said, I'm not so sure that it's in the end relevant. For one thing, because I don't actually believe that there's a final theory. I already said
Yeah.
this.
Yeah.
Just think like we will find something wrong with quantum mechanics basically, and all this
Yeah.
final theory stuff will go out of the window. And then there are things like, for example, in Gödel's theorem. I always wonder, like in practice, how relevant is it actually? Because suppose you have this one statement that you can't prove to be true. What will you
Mhm.
do as a physicist? Well, you would go and see if it's true by making a measurement.
Yeah.
If you can make a measurement, like if you can't measure it, who cares? If you can measure it, you check it. So if it's true, you add this as another axiom, right? So
Yeah.
this is how it works. So you know, I
Well,
have to say that I think most physicists won't be terribly impressed by the paper, but I quite
no.
like it.
Well, I have, even though I'm one of the authors, I also have mixed feelings, but I partly, again, it was my confirmation bias. I go back to 1984 when I was old and you were a baby. Um, uh, when when string theory was not called string theory. It's called the theory of everything by absolutely every practitioner who was working on it. And in fact, even if it were a theory of everything, it would actually be a theory of very little, as Frank Wilczek used to say, because you know, quantum gravity is incredibly important for understanding the beginning of the universe and the ends of black holes, but not for understanding how water boils or oatmeal boils or any of it. You know, most of the things are how to build better materials and many of the things that matter in people's lives. But I did like I I do like various aspects of this because I'd like to hear people stop using the term theory of everything. But the idea is that if the way I think of a theory of everything, if you had it, is that you have a theory that can allow you to calculate in advance anything you could see. Calculate in advance and predict any measurement you could ever do. That would be a complete theory. There's nothing that one could ever see or do that this theory would not allow you to predict. That's kind of and on any scale in the universe. And there are fundamental, as you point out, mathematical arguments that are quite profound in some cases that basically say that's impossible. And I think that's really interesting. Uh, as you say, I get your point about Gödel is very correct. There are some things that are true that you can't prove to be true. It's also it's more explicit in Tarski's theorem. There's three theorems: Gödel, Tarski, and Chaitin's, that we talk about, but they all are different aspects of incompleteness. And then physicists would add that as an axiom. And all we're saying is yes, it would be we call that a meta theory. So you can't algorithmically start from a certain set of rules and derive everything. You basically there's some things you couldn't derive, and then you want to add them, and there may be an infinite number of things you have to add. Who knows? But and so that's interesting in a general, maybe I hate to use the word philosophical sense, but in a general sense for the limiting the claims that science will ever be over in that sense. Now, you may argue that the direction science going in isn't important anyway, but 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 I like to think of it as cosmic job security. That there'll never be a theory that allows you to predict everything. You'll have to do more experiments and discover that you'll have to keep looking. And thinking alone won't do it. You'll have to keep looking, and that's great because science at its best involves looking and discovering things about the world. And the thing I like about that last part of this incompleteness theorem is that, and because it does relate to a lot of the claims of quantum gravity, and there's so many claims and so much hyperbole, as you know, about string theory and loop quantum gravity and all of the rest. But one of the aspects that's relevant to black holes is thermalization. And one of the interesting things that I hadn't realized till we were working on this paper and I didn't know enough about it. But the process of thermalization has been shown to basically be undecidable in a fundamental mathematical way. When a system will thermalize is kind of like the same as knowing when this computer program will shut itself off, and you can't, and that depends upon the complexity that you don't know in advance. You don't know how much complexity you have to understand and whether you'll, that was the argument you gave at the end. And so it does relate in a to me, at least in a real way, to some of the directions that people are going in quantum gravity, which is that if thermalization in the neighborhood of black hole, event horizons, and all of that is important, this may actually come back and bite you in the face, that the theory may not be able to actually tell you something you're claiming happens, that you may not actually be able to ever really fundamentally calculate from first principles. So it may have a practical significance, it may not, but you're absolutely right. From it's like everything related to the theory of everything. When it comes to something, it's probably doesn't matter very much. As again, as Frank used to say, I don't want a theory of everything. I want a theory of something. And and theories of something are particularly useful. Theories of everything are fun for some people to talk about. And like you, it was fun for me to come up with to write something and basically argue that even if you like it, it can't happen. Anyway, I don't know if we illuminated anything. Any comments based on what I said or no?
No, just a question. The paper that you mentioned about the thermalization, was this the recent qubit paper or
No, no, no. There's
no,
another
it
paper.
was a
It's about
different one?
in undecidability theorems.
All
The
right,
Chaytons, they're
interesting.
applying.
Maybe you can send me a reference because I must
Yeah,
have
I'll send
missed
you a
that.
reference because it
Yeah,
was I
okay.
didn't know about this field enough to and my colleagues did, and I learned about it and we reference it in in
I
some
see.
point in our
Well,
paper.
I've looked at all these papers where they claim there's a physical quantity that we can't compute, and it's always the same. And in all the papers that I've seen, is that some physical quantity becomes infinite, like it's an infinite number of particles or something like
Yeah.
that. So it's not actually a real system. So far, this has always been the case, which is why I want to look at this paper.
Okay, well, it'd be worthwhile looking at this one together. I have to say, I've written some papers of mine, some of which have had a great impact, which I didn't understand at the time I wrote them, and fully. And this one is one that I've had to come to grips with a lot. I'm not sure I even still fully understand it. I'm not sure this one is going to have the same kind of impact as some of the other ones, but it was fun to learn some of these things because I tend to ignore. I mean, Gödel and these incompleteness theorems are very important, but because, as you say, from a practical perspective, I'm someone who likes to just do things, and it often seems a little ephemeral. So I haven't thought about them in detail, and this forced me at least to think about them in detail a little bit. Okay, anyway, thank you for the advertisement, and I appreciate it.
Well, a lot of
Um,
people asked me to discuss this, so yeah.
well, I've now learned if you put theory of everything in a paper, everyone, all these people in the public want to hear about it. But anyway, now I will talk about something that's much more grounded, perhaps the most grounded calculation in elementary particle physics, the thing that made quantum field theory put it on the map. One of the two calculations is something called the G minus 2, in this case, G minus 2 of the muon, the magnetic moment of the muon. Elementary particles are charged and they behave like they're spinning. And a spinning charge will have a magnetic moment. Now, they're not really spinning, but quantum mechanics says they behave like they're spinning and they have a magnetic moment. And because they have a, their charge, which is quantized, and their spin, which is quantized, you can get a number for the value in in terms of some fundamental unit called the Bohr magneton of the magnetic moment of elementary particles. And if all things were just simple, the number would be 2. Doesn't matter in those units, or a half, or depend what unit you pick. Um, but of course, the great thing about quantum field theory is it says that there are actually all sorts of virtual processes going on where a muon isn't just a muon, it's emitting a photon, and then for a while it's 2 muons and a muon and an anti-muon. And on small scales, lots of strange things are happening. Virtual processes that make the vacuum of elementary particle physics strange. And many people say, well, that can't be true. But of course, the beauty the real beauty in the 1947, 48, 49 was you could actually make prediction. You could actually calculate results in spite of all the craziness that's going on at small scales and make predictions of what the quantum mechanical corrections are to this number 2. And it is the best prediction in all of science in the sense that from fundamental principles, you can make a prediction of a number to almost 12 decimal places. And the other amazing thing, which I think is even more amazing as a theorist in particular, is that experimentalists can measure certain quantities if they're really clever to 12 decimal places. And there's nowhere else in science where a fundamental prediction that's that's all the way to 12 decimal places can be compared to theory to 12 decimal places from fundamental principles. It's really, in my mind, one of the most beautiful things in physics that you can actually make a fundamental prediction and test it. And it really tells us that empty space is really weird. And so the G minus 2 of the muon is incredibly important because it validated the whole computational scheme we use to try and understand elementary particles and fields. But what makes it even more interesting, and what's made it more interesting for 40 years, is because the quantum corrections are sensitive to weird processes. If there's any new physics, like supersymmetry, which has new elementary particles which can be emitted by muons and then absorbed at very small levels, giving very small effects. But if you can measure something to 12 decimal places, maybe you can look at those effects. In fact, many people have argued, why build a big accelerator when you can look for effects that come in at the part per billion level in a very sensitive experiment and then do the experiment. It's not a tabletop experiment. These are big, many meter long storage rings of muons, and it's still less expensive than building a new particle collider. And so people have argued, hey, maybe this is a great place for new physics. In fact, I've forgotten this till till just now, but I actually wrote a paper that's sort of significant on the one of the first calculations of the G minus 2 of the muon and supersymmetry theories. I totally forgot that. But anyway, um, and uh, and so it's incredibly interesting. Now, what made it more interesting, at least from a fundamental perspective, is it looked like there was a difference between the theoretical prediction and the observations in the 12th or in the 10th or 11th or 12th decimal place. And if it wasn't so beautiful, you'd say, who cares at the 10th, 11th, 12th decimal place? How am I going to believe something like that? But you can. If there was a known, well-defined disagreement statistically between the theory and the observation of 12 decimal places, it would tell us there's something new. And supersymmetry predicted such a difference. And for a while, it looked like there was such a difference. And people have been doing these G minus 2 experiments, colleagues of mine back when I was at Yale, their whole careers, and they're beautiful. They really are beautiful and very clever experiments. You basically, the idea is basically if you have a magnetic moment and you have a magnetic field, then a little magnet will precess, and the frequency of its precession will depend upon how big a magnet it is. That's the basic simple idea. And so they take muons and store them and see how they precess in magnetic fields and look at the radiation they emit, more or less, or the exact. And it's like NMR. It's very precise and allows you to do unbelievably good experiments. And the most recent, and people say final G minus 2 experiment was just done at Fermilab. I think the magnet was taken from, you need large magnets for this, was taken from Brookhaven National Laboratory, another accelerator in the United States, to Fermilab and built and it stored 300 billion muons. Remember, muons only live 1 second long, but if you accelerate them enough, they live a little longer. And so it's hard to store them, and there's 300 billion of them in this big magnetic field. And they finally measured the answer is, and the correction to this number 2 is point, and I have to say it because they work so hard to get the number, 0.001165920705. And that's known with an accuracy of 127 parts per billion. The prediction is 0.001165920033 with a theoretical uncertainty of 540 parts in the last three numbers. And unfortunately or fortunately, it agrees. The theory and the experiment agree. Now, having said that, there's one little additional technicality which is kind of neat, which is how do you calculate? What's the uncertainty in the theory? How dare you say theory has an uncertainty? Well, the uncertainty comes in the fact that muons, which are only experience the weak force and the electromagnetic force, nevertheless can emit quarks, which experience the strong force, and we can't calculate with the strong force. So we have to make approximations. And for a long time, people made approximations based on measurements, and they kept giving the wrong answer. And what's really fascinating is, well, one way to calculate is put it on a computer in a lattice and make space a lattice, and then let the computer do detailed calculations on a lattice. And it turns out those lattice calculations give answers that are different than the other calculations and agree with the observations. And initially, that was a big deal, and people didn't believe the lattice calculations, but now more people have done them. And now it looks like the computers are smarter than we are in that sense, or at least they're giving an answer that's in agreement with the observations. And why extrapolating results from other data from other experiments gives the wrong answer is not yet known. But the bottom line is, at the end of all of this amazing bit of work and real solid work by theorists and solid work by experiments, we made the best measurement that's ever been made, and the theory agrees. And many people are disappointed, of course, because there's no evidence for supersymmetry or anything else that people thought might come out of it. But even though it gives a null result, I wanted to herald it because I think it's in some ways science at its best. Turning it over to you.
Well, that was a very nice speech. Yeah. So I'm kind of super unsurprised by this because one could see this coming for like 10 years or something. Yeah. And I think there's a deeper lesson in this, which is that you said some people have argued you could replace to some extent building bigger colliders with making high precision measurements at lower energies. And this is the sort of problem that you run into, because you'll have to do these calculations very, very precisely. So you put the burden on the theory.
Yeah.
Whereas if you go to higher energies, if there is a signal, it tends to be in your face. In some
Yeah.
sense, once you have collected enough
Good.
data, you have a bump. That's the
Yeah.
exposure,
Good point.
basically.
Yeah.
So it's a somewhat cleaner signature. But yeah, I mean, it's a great achievement. I mean, I can remember people discussing the Muon anomaly since I've been in physics, basically.
Yeah.
And so I'm quite happy we can lay it to rest. Though I have to say that, I mean, you only told like the good side. So I think it also has like a negative side, which is that, from the people that I've personally um known and talked to, I think no one actually believed it was some physics beyond the standard model stuff. Like everyone, maybe that's a generational thing. Like,
It is.
put
It
the
is a job.
blame on the theoretical calculation, or maybe it's something to do with the kind of people that I tend to know. But the idea that is kind of a new particle, it's a fifth force, or it's extra dimensions, and I had a student who wrote a paper on that, so
Yeah.
on which I'm a co-author, so I'm also guilty, right? Um, so that attracts much more attention, like in the headlines. So when a newspaper writes about wrote about the
Yeah.
G-2 anomaly, they write something about evidence for a fifth force or something
Yeah.
like that. The standard model is broken, stuff
Yeah.
like
Yeah.
that. And that attracts a lot of attention, not just in the general population, but also among physicists. And I think it inspires them to make up more stuff. And so it becomes this self-running thing.
Yeah. Yeah.
So I think that there's this community dynamics, which is something that I really don't like. So I'm quite happy that we can finally put this to rest.
Well, I don't know what I warn you, nothing ever gets put to rest finally. But anyway, but look, I'm sympathetic with you there. But look, I'm telling you, I'm of a generation where I attended many meetings where a certain group of people would say, "This proves supersymmetry. This anomaly in the G-2. Here's our calculation. Look at the anomaly. It proves that supersymmetry is true." And I'd hear it over and over again. I didn't believe it. But and so so it has been useful to close certain doors. But I'll also say you're right. But you come from a generation of people saying, "Oh, an anomaly, let me invent some crap, some nonsense crap," and that's true. But let me play the other side of the devil's advocate. When I did this was in 1985, 84, 85. That we did the calculation of G-2 in supersymmetric theories. And it was what I liked. It was one of the I liked it because it was most honest and certainly difficult. It was the most complicated calculation I'd ever done and probably have ever done. And I did it with people I could never have done it alone. I did it with a colleague, Noriska Sakai, and others. But he's a Japanese physicist, and it required keeping so many terms that I couldn't even write them neatly on a piece of paper. But he would store them. But what I loved about it was a concrete theory, low energy supersymmetry was a concrete theory. If you wanted it to explain data, it was highly constrained in certain ways. And therefore, if you worked hard enough, you could make a concrete prediction. And it was for me, that's the most satisfying. That was an extremely satisfying thing was to take a concrete theory, which was beyond the standard model at the time, and and make a concrete prediction. It just required a lot of work. And so for me, I think I was trying to convince my colleagues that I could be an honest, hardworking theoretical physicist. I had a number of colleagues like Joe Bulczynski and Mark Wise at the time at Harvard, and who basically said, you gotta prove yourself by doing this calculation. So anyway, I think it's nice in an era where science allowed you to make concrete predictions, even for well-motivated new physics, and then compare them to theory. The problem is what's happened is things have become so difficult, and the standard model is so good that people now are of a generation, and your generation, I think, that tend to say, "Oh, let me just invent the wildest things in the world to explain everything with no constraints on parameters, and every new every new result can be new dimensions or this or that." And yeah, I have the same kind of feeling about all of that, which is that it's much ado about nothing. I don't know if I'm over stressing, but so anyway, I think G minus two is an example of, maybe we can put it this way: G minus two is an example of physics at its best, and maybe physics at its worst. But it's wonderful when good theories can be tested with good experiments, and one hopes that's true in all areas of science. Maybe we can end on a positive note. Is that acceptable?
Yeah, let's talk about the future. I want to
Yeah.
talk about AI, and maybe more generally, want to hear what your sense is what AI is going to do to physics. So, in the past months, there have been several developments with self-improving AIs. Maybe the biggest headline came from Google DeepMind, Alpha Evolve.
Yes.
It's basically an artificial intelligence system that mutates code and then tests the code and improves it. So I was quite impressed by how successful it was at improving the code, and also that it made some actually useful discoveries. Like, one of the things that they found was a better way to multiply big matrices, basically. That's more
Yeah.
efficient than anything that was previously known. So no
Mhm.
humans can come up with it so far. And this thing kind of did it within, I don't know, a couple of days. God knows. I didn't look exactly at the numbers, because we can quibble about, do we actually count the time that they put into to construct the thing or something like that. But it doesn't really matter. So it found something really new. And it's quite interesting, because matrix multiplication is one of the operations that you need to do in a lot of those models, right? So it, in some sense, it did improve itself, or at least other AIs.
Mhm.
And so this is one of the steps towards what's been called the intelligence explosion, formerly known as the singularity, when AIs can improve themselves, so it becomes this self-running exponential process, of which we don't know the endpoint, hence the singularity. So I'm not saying that we're anywhere close to that point, but what we're seeing right now is that people are trying to use these evolutionary approaches to do exactly that. And of course, that isn't a new idea, but it's kind of like this idea of the neural networks. Also isn't really a new idea. So in the end, I think what was the inflection point for making this work was just computing power. Okay, so I'm
Yeah.
greatly oversimplifying, and everyone who works on the topic will hate me for saying this, because of course there have been many, improvements on the code and insights and blah 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 blah. But basically, what's driving the whole thing is computing power, and that more people can use it. And if more people can use it, they can work with it. They have more insights. And so naturally, like, this makes me wonder, like, what's it going to do to science?
Yeah.
So one thing that we're already seeing right now is that these models are becoming really, like, not large language models, but some of the stuff that DeepMind's working on, and actually also some of the large language models like O3, like GPT-O3, they're becoming really good at math. And so I think some mathematicians are actually spooked by this. They see, like, these models have eaten so many proofs, and it's kind of a language, right? And but it's a very clean language, like, it's not
Yeah.
contaminated. Of course,
Yeah.
they're wrong proofs, but
Yes.
mostly I think maths is fine. So
Yeah.
they can learn this very well, and they're becoming really good at covering topics all over the place. So, and I think it's quite possible that a lot of what pure mathematicians do right now will, in the soon future, be replaced by AIs, the same way that we once had human calculators that were crunching the numbers, with logarithmic tables and slide rules and stuff like this. And it doesn't exist anymore, because we now have computers, right?
Mhm.
And so I think that that's what's going to happen to mathematics. I'm not saying that all mathematicians are going to be replaced by AI. I think that's a little bit more in the future.
Mm. Yeah.
But what comes after mathematics? I think that will be physics. And so that's the question, like, how much can it do? So, we want to hear your opinion about that.
Well, okay, that was a great introduction. I looked at the paper that you referred to me, and I confess that I didn't understand it all, but I found it fascinating and terrifying. And I'm not really often terrified by AI, but and in some sense, in reflecting, it's not surprising that that a code, which is actually what it is, it's like Feynman used to say quantum computers will help us understand quantum mechanics because they use quantum mechanics, and that's right. And if you think of a large language module or these AI things, they are based on matrix multiplication, and so it's not too surprising that something that has huge data inputs for learning would be able to prove the very process by which it's learning, because that's what it's doing. I mean, if it's using these things, and if it's evolving to find techniques that do it faster, well, it's the first thing it's going to find is the techniques that it's using. I mean, it's not too surprising that the first area that it kind of evolves in to improve is computations of the type that are central to its existence. But it is fascinating to me because, of course, if it improves code, and what's really nice is then you use empirical evidence. You run the code and see if it does a better job. So it's not some sort of internal calculation. Then you're sort of doing science. That it's doing its own experiments, and self-programming, improving AI for me was the future that I've always said. Once you have a self-improving AI, self-programmable improving AI, then I fully expect it to develop much faster than biological systems because there's no constraints on it that way. And this is an example of it. And you're absolutely right. The fact that it found a better method, if you wish, for matrix multiplication, or looking for eigenvalues in matrices or whatever, um, is interesting. And as I point out, what makes it more interesting is just the fact that it will improve your ability to do this, because if you can find a more efficient mechanism, the whole thing about LLMs and all this is they require huge computing resources. That's why, I don't know whether it's um, Amazon or whatever, or Google, they want to have their own nuclear reactors for power because they need so much power to do these damn things. But if you can improve, as they said, I think they improved some algorithm and made it 25% more efficient, I think is what it would said. So I think that's the number, what's interesting is it turns into ultimately requiring 1% less energy, I think, was, if I read the article right. And that may sound trivial, but if you're using a hell of a lot of energy, 1% less energy means, or 1% fewer number of computers, that can actually be real significant dollars. And so small changes in efficiency can be huge monetarily. And that could mean that these systems, if they become more efficient, are more accessible. Because I think one of the other areas that, I'm not as worried about singularities as people are. Um, these are good for doing certain things, as you point out, matrix multiplication and proving mathematical theorems. Um, but they're not good at other things. So they're really good at certain things. They're not general intelligences that are good at everything. But one of the other limitations on them is they're not tabletop. You need incredible computing resources to do this. And it's not the kind of thing that can be done cheaply or mass produced. And therefore, that's good in one sense and bad in another. It's bad because the only companies that can do it are the ones that are rich enough, like Google or whatever. And if they're the only ones who have smart enough LLMs, then they have a monopoly on producing money. And one worries about what's going to happen there if AI, and I think it's quite likely that that's exactly what's going to happen, that AI is in the province of the richest companies, and those richest companies are going to put a lot of people out of work and make a lot of money, and then that money won't be distributed among society, and that's going to be a huge problem. But aside from those societal things, the fact that this self-improving programs are working so well is really impressive and a little bit scary. And I was going to ask you, it I think the Alpha Evolve group is part of the group that was using these techniques in chemistry. Were they not part of the group that used these techniques in chemistry that caused the people in DeepMind to win the Nobel Prize in chemistry? Looking for new. I think they were the ones who were looking for new configurations of large scale molecules and new chemical techniques to find certain things. Anyway, I think it's the same group within DeepMind, but I could be wrong.
It's possible. I didn't look exactly at the names of the people who were involved, but they have a lot of alpha things. Like they have alpha proof, they have alpha
Mm.
evolve. Alpha
Yeah,
fold
there's
is the thing with the proteins, and there were a couple of other alphas. So it's probably, if not exactly the same group, then like
yeah,
a
yeah.
lot of overlap
Yeah, there's
between
probably a lot of
what
all,
they do.
but
Yeah.
I think the point that you made and the point that's inherent here is quant both quantum computing and AI, in my mind, will be the most immediate benefits will be for detailed scientific calculations, and 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 that's what's happening. And in terms of the implications of society as a whole, I think a lot of people, it's science fiction, a lot of that. But for improving the ability to do calculations and predictions, and that's a good thing in general, I think. That's why I'm not as afraid of AI as some people, because I think it'll help us. I hope in the long run it'll help us more than hurt us, except for those socio-political things I talked about in the end, where certain companies basically become so ultimately infinitely rich that they don't know what to do with anything. Yeah.
So I totally agree on the economic problem, but I want to come back to your lack of worry about what's going to happen to physics. Maybe that's because you're not a student at the moment. Because think
Uh,
about your calculation with the super symmetric
Symmetry, yeah,
contributions to the
right.
mu and g minus two. I think it's totally realistic that in like 2 3 years, or maybe even sooner, that calculation can be done by an AI. So
Oh,
you'd
I'm
be out
sure
of a
it can
job.
already be done. I bet it could be done much better by an AI, and even maybe you don't even need an AI, you just needed a faster computer. But yeah, you're right, that is a problem, except let me say why I'm not worried there. I'm not worried there because I believe that science, including physics, is empirical. And so, since I think that what drives physics is not theorists like you and me, for the most part, it's experiments, that as long as we keep building new machines that give us new windows on the universe, then calculations aren't all of science. It's looking out and being surprised. And so, since you can't train AI on things we haven't yet seen, I have hope for science, because as long as we keep looking, we'll discover things we haven't yet seen, and that means that AI and theorists are not going to take, that means cosmic job security. What do you think of that?
Yeah, no, I agree with this for the time being. But you've just discarded all theoretical physicists.
Well, in a sense, I have, but I think, yeah, okay, and that's okay. I mean, I don't have a problem in the world if in 10 years the best theoretical physicists in the world are computers. I mean, from the point of view of knowledge, that's a good thing, and I don't think it'll be 10 years, by the way. So I think it's still worth doing a PhD, but but again, I remember having this discussion with a mutual friend of ours, again, Frank, um, a long time ago, and the question I and it'll be fascinating, because the question will then be, what physics questions are of interest to this computer? What can you learn from it? Will its interests be the same as ours, and what can I learn from it? And if I'm interested in learning about the universe, and I have a better colleague that's a computer, well, okay. I mean, the world is gonna change, and that's okay. Technology changes the world. It doesn't always make the world worse. That's my point. Having a phone has changed my life. Having a smartphone has changed my life. In many ways, it make it worse, but in a hell of a lot of ways, it make it better. And so, um, you know, to I guess to say the future is always dystopic because of the new technology is not always clear. Nevertheless, I think the future is miserable, so I guess it doesn't matter in the long term. In the long term, most of my science has been to say, in the very long term, the future is miserable. So enjoy it while you can. Now, speaking of enjoy it while you can, the last topic, I always like, I like thinking about the origin of life, but I decided not to do any biology. I want to do physics-ish kind of stuff in this, but it's still a fascinating result. I've said over and over again that astrobiology is the most hyped area of science. It's not, most of it isn't even science. It's just pure speculation about things we know nothing about. It's fascinating to think about and talk about, but these people who claim to talk about it with authority are usually bogus. What we need is data and experiment, and there's so much we don't understand. And what I liked about this little result, which otherwise wouldn't have gotten a lot of hype, is is article entitled "How Organic Molecules Survive in Space," and it's important because I have little doubt that in the origin of life, the basic building blocks came to Earth from space. And not like, I'm not talking about panspermia where, cells and living beings came from elsewhere. Maybe that's true, but the organic materials, and in particular, these organic materials called polycyclic aromatic hydrocarbons, which are ubiquitous at the basis of ultimately DNA and life. Yeah, and what's interesting is these materials exist in interstellar space, and molecular clouds are produced in stars and then emitted in supernova explosions. But the point is, they're not supposed to exist because a supernova explosion and the subsequent stuff that goes out is a pretty drastic event with lots of ultraviolet radiation and lots of molecules colliding. And it's not a nice place for simple molecules to survive. They get torn apart. They get banged into and they vibrate. And so initial calculations said these small polycyclic aromatic hydrocarbons, PAHs, like something called indene, which I think is something like what is it? It's C9H8. There's just hydrogen. It's a great place to find hydrogen. 9 carbons, 8 hydrogens. These kind of things, if they're small, then collisions will break them apart. If they're large, it turns out that they're so large that the vibrations are so complicated that they won't break them apart. But these small ones are observed, and the James Webb Space Telescope observed them. And that may be vitally important for the origin of life, because if they didn't survive longer than we expect, then maybe the conditions on Earth wouldn't have been uh, good for life to form. And what's kind of neat is a simple result and a simple experiment. Yes, they're observed at a higher abundance, and people actually did an experiment on Earth with a in Switzerland, I think it is, or Sweden, one of those two places, Sweden, Stockholm, with a storage ring that would actually be able to take these things and recreate the conditions of molecular clouds and try and find out when you shine ultraviolet light at them and when they bang together, why they survive. And they survive because of a process called recurrent fluorescence, which is kind of neat to me as a physicist. It basically says you have this molecule vibrating, and if it vibrates enough, it can actually translate that vibrational energy, which will otherwise break it apart, into exciting some of its eternal electric degrees of freedom, which then relax by emitting a photon. So it can get rid of the energy that would break it apart by turning it into a kind of energy that you can emit it at the speed of light and get away. And the new calculations suggest it's possible. And then when they actually did the experiment, they discovered that indeed this energy that would otherwise break it apart relaxes 5 times faster than you'd imagine, and the thing could survive. So it's a little teeny result, but physics and science grows on baby steps. And that little teeny result may result in the reason why you and I are here, which I find it fun. It's not some grand theory of everything. It's a little baby result, but maybe that little baby result, which happens by an obscure chemical or physical processes called recurrent fluorescence, which I'd never heard of before. Maybe that little baby result will result in you and me. And I think that's the kind of a beauty of science. So I thought I'd end with that one.
Mm. Yeah, no, I find that super interesting. I like these studies because I keep thinking if we figure out how life on our planet starts, that will tell us something about the way and possibility of life to start on other planets as well. And I certainly hope that at some point we'll find life on other planets. And I don't mean microbial lives. I want something that can walk around.
Well, it'll be an AI. But anyway, but in the long run, maybe it will be. But yeah, of course, we all want that. But I think it's important is to get, and this I want to stress over and over again, is to get there. Don't listen to people who say, "Oh, I have evidence for life on Venus," which turns out to be garbage. It's these little teeny experiments which tell us more about the fundamental science of how life may have evolved on Earth that in the end, in my mind, will help us much more as scientists know where to look for life elsewhere in the universe than people making grand claims about this or that. And so it's real solid science, and that's science. Not much of what you read about in astrobiology is, in my mind, science. I'll say it again. I love talking to you, Sabine. It's and I love listening to you. Obviously, I love talking at you, but I also love listening to you, and it's always illuminating. And this was actually, I think this went much better than I thought it would. So thank you very much. I hope you had fun.
Yeah, no, it was great.
Hi, it's Lawrence again. As the Origins podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture. You can learn more about our events, our travel excursions, and ways to get involved at originsproject.org. Thank you.